Let's do this thing on this beautiful, beautiful Tuesday.
Oh my gosh, diagrams.
I know, right? Can you believe it? But before we get to do that, I want to say that next Tuesday's class will be on Zoom only. I know, because I'm playing hooky. Well, I'll post the video after, but it will only be on Zoom. But I'll do my face and properly, you know. Hey guys, today I want to talk to you about combinatorics. I know no one's gonna ask what I'm doing.
What are you doing?
What am I doing? I'm going home to visit my husband because he's going on a deployment and he won't be back until June. So I'm taking that opportunity to just go on Zoom for that one day. Okay, so I'm just realizing I meant to put that on Moodle, but I'll do that now that you know. Now you won't be so thrown off. I don't feel terrible because you guys are the only ones that really show up. So now you know that you can just go on Zoom. And so Zoom only. Well, and video after. I guess I shouldn't startle people.
And that's just for you.
It is a new section, but it'll be a bonus question on test 2. It's going to be a real question on the final exam, but then we'll have time to go over it and just kind of solidify it. So I'm not going to do, you know, a weird class and then have it on the test, but it will be a bonus question. Zoom only on Tuesday. Okay. On section 7.5, which is combinations, which the reason I don't feel, well, I don't feel terrible at all. But one of those reasons is because we're basically going to do combinations today. And so in a mini way. Okay, and then we're going to extend it as we go through the rest of the chapter. So section 7.5 is on combinations. So on Tuesday next week, we're going to do 7.5 on combinations, which will be a bonus question. Bonus question on test 2. Because we have our test 2 on the Thursday, and it feels pretty rude to introduce a topic on the Tuesday and then test you on it on the Thursday. So that's why it's going to be a bonus. And then you'll have seen a test question at least, and opportunity for bonus marks. All right. Any questions before we do more counting? So counting, it sounds silly almost, right? But counting is really difficult, right? Not the straight up, hopefully not the straight up 1, 2, 3, 4, but if we have to count combinations of things, and that's why I say, okay, we're kind of introducing combinations today. And so one type of counting we need to be able to do is counting combinations or counting possible combinations. Lots of different examples, but most commonly, right, if we have, you know, some outfit choices. How many outfits do we have, right? Those are different combinations of, in this case, we've got 2 blouses and 3 skirts. And that's it, I guess. How many different outfits consisting of a blouse and a skirt can this person wear? Okay. And so if you think about this, there are a number of different ways that you could tackle this problem, right? It's just problem solving. But the goal is to count how many outfits there are, right? How many possible outfits. So we want to count the number of outfits, right? Given some criteria. One way that we could do it is we could say, well, she has to wear a blouse and she has to wear a skirt. That's kind of implied because it says so right here, consisting of a blouse and a skirt. Okay, it doesn't matter which one she picks first. And so in that scenario, how about we just say, okay, first she picks a blouse, right? And one of the common ways that we could kind of visualize the choices is with a tree diagram. And the tree diagram is going to look something like this, where first she picks a blouse. All right, so this is going to be my blouse layer. Blouse. She either picks blouse number 1 or blouse number 2. Next kind of decision point is, okay, now she has to pick a skirt. Okay, she still has, so it doesn't matter which blouse she chose, she still has 3 options for her skirts, right? And so now we can make 1, 2, 3 branches for the skirt. That's for blouse 1, but if she chose blouse 2, she still gets to choose from those same 3 skirts. And so, wait, 1, 2, 3. And we can call this S1, S2, and S3. S1, S2, and S3. Just generic labeling for a blouse and a skirt. Now at the end of each of these, right, then we can list all the different outfits, right? Blouse 1, skirt 1, blouse 1, skirt 2, blouse 1, skirt 3. Then moving on, blouse 2, skirt 1, blouse 2, skirt 2, skirt 3. So usually what we do to summarize the outfits is we say, okay, well, this is going to be B1, S1, B1, S2, B1, S3. And I guess I should have used subscripts, but I'm too far gone. B2, S2, B2, S3. And I'll move this outfits up here. There. So now I can count how many combinations I have, right? How many possible outfits? 1, 2, 3, 4, 5, 6, right? And so we have 6 different outfits. How many different outfits? Right? There are 6 different outfits. Therefore, there are 6 different outfits. I think I meant to develop this concept a little bit deeper, but we'll keep working with the tree diagrams. But pretty quickly, I'm going to move towards what I call slots instead. And so I want to introduce those almost right away, because whenever the questions say make a tree diagram, unless you have to list all the possible outcomes, which you do in one of the questions, pretty sure, right, then we're really just looking for how many different combinations do you have, right? And if you think about, okay, so pretty much every day, and I'm so weirded out because there's this stain here, but look down, there it is. That's why I haven't worn it in a while. I know what you're thinking. Wow, shouldn't you just get rid of it? Yeah, probably. It's right here.
Oh, that's good.
I know. I know. Isn't it so offensive?
I turned my shirt pink and I still haven't gotten.
You know what? I think you're onto something. Maybe I should just turn it a different color altogether.
Wash it with black and gray.
Gray with
Or
pink.
have
It
you
looks
tried
terrible
bleach?
now. I still
No.
It's just not.
I have not.
Have you tried bleaching yours?
No.
Bleaching the white sweater?
No. I also know I got this in 2012, so I feel like I could probably thank it. Well, besides the stain, yeah, it's great. Anyways, if I think about a typical day, I wear a sweater, a shirt underneath, and jeans. Let's say I have, I don't know, 20 sweaters. What's reasonable? 20 sweaters. Now imagine your tree diagram. Instead of 2 cute blouses to choose from, you'd start with 20 branches for the sweater. And then after that, you have to choose a shirt underneath, or maybe you don't, I don't know. But even make it easy because I only have 1 pair of jeans that I use. So then after that, it's just 1, but still. I'm really sharing my dress secrets. Anyways, there are no secrets. But that tree gets out of control, right? Really quick. And so usually what I do, instead of visualizing with a tree, I use these slots instead. Okay. And so instead of a tree, we can calculate the number of combinations using slots. I'll put quotes around that because that's not a technical term, and I don't really know what to call it, but slots. And what that's going to look like is I'm going to have a slot for the blouse, right? I have to pick a blouse. And pay attention to that wording, right? And I have to pick a skirt. And maybe I should make some room here. And a skirt. The reason I mentioned this and is because that turns into multiplication. Wow. So if you catch yourself, okay, this has to happen and this has to happen, then you're going to multiply those things together. When we use and, we multiply. And I guess, spoiler alert, if you catch yourself saying or, then you're adding those 2 things, okay, because they're 2 different outcomes. But we're not there yet. So here, what do I put here? So I've got a slot for my blouses. That's going to be the number of blouses that I have to choose from, right? And so here I have 2 blouses to choose from. And I have 3 skirts to choose from. I'm trying so hard not to get ahead of myself. We can even do conditional things like, what if one of the skirts you can only, or one of the blouses you can only wear 2 of the 3 of the skirts, right? So we can make adjustments like that, but we'll see. We've got examples of that, right? But level up pretty quick. So here we have the number of blouse options. And here we have the number of skirt options. But we still get 6 outfits. So if you like the tree, that's great. If that makes sense to you, all right, then go for it. But I'll try to use both as much as possible, just so you can see them working in tandem. But you only have to use one of these, right? You don't have to use a tree. A lot of the questions say use a tree to figure out how many different options there are, right? But you don't have to. You can just do the slots if you want to. Just multiply. What we just established is called the multiplication axiom. I know, fancy, right? And so it says that if I have some number of choices followed by the same number of choices again, or regardless of what choice I made first, then we can multiply those all together. And that's the multiplication axiom. So here, do I have it? Okay, well, I do have it here. So let's do this example and then I'll bring this one in. Just keep the order. Because this page was not behaving at all. I feel like, yeah, if a person, maybe, because men are allowed to have blouses too. If a woman has 2 blouses, 3 skirts, and 2 pumps, because it's the 80s, I think. Which I think is the last time we wore pumps, right?
Prince.
If Prince has 2 blouses, 3 skirts, and 2 pumps,
That's right.
how many different outfits consisting of a blouse, a skirt, and a pair of pumps can you wear? Prince. Because I'm running out of space here, this is the end of the page. Let's use the slots first. And then we can make our tree to confirm that we get the same number. Okay. And so how are you going to set up your slots? You've got a blouse and a skirt. Usually I don't write the and. It's kind of implied. But if it helps, then you can write it. And pumps. She has 2 blouses, 3 skirts, and 2 pumps. Pumps. I'm staring down the barrel of 12 outfits. Let's confirm with a tree. We can confirm there are 12 outfits with a tree. I'll do them in the order that they appear, right? I'm gonna start with 2 blouses. Now you wanna make that first set of branches super wide because there's a lot coming off of it. And so, did I make it wide enough? Blouse 1, blouse 2. Off of each blouse, I have 3 skirts. Skirt 1, skirt 2, skirt 3. Oops. And then to top it all off, I have 2 pumps. 1, 2. I'm just gonna do little shorty branches. And then Prince has 14 earrings to choose from. Oh no. I was just layering. Then you'd have 14 branches off of each of those branches, and that's a no for me. But it is a way that you can count any sort of combinations, right? Especially if you do have restrictions like, okay, how about if you choose blouse 2, you cannot wear skirt 1, it just doesn't work, right? Then you would eliminate this branch, right? And so the multiplication axiom works if it's always the same and there's not really restrictions that don't apply across the board. Okay? And but the tree would work for kind of more complicated scenarios. But you'd have to draw it out, and that's annoying. P1, P2, P1, P2. Do you guys even know what pumps are? Yeah. It's like a high-heeled shoe that is not quite high-heeled. It's like chunkier heel, I want to say.
Yes.
Pumps. My mom used to wear pumps. They'll be back. So, yeah, it always comes back. I know, I saw a girl wearing a shirt today that was like, I had a shirt just like that, but like 20 years ago. And that's upsetting. I just gotta ride it out. That's what I should do.
I needed this one.
Yeah, this is so a la mode right now. No, they always change something. Like you can just tell. Oh, I didn't even finish. I was so over this tree. Boring. Anyways, we have how many? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outfits. I'm not going to list them all, but you could, right? Using the tree, you are able to list all the different combinations in your outfit. Okay. So now let's introduce the multiplication axiom, which we've already seen. If a task can be done m ways and a second task can be done n ways, right? And these tasks can be blouses or skirts or whatever, right? And so we use tasks generously. Okay? Then the operation involving the first task followed by the second can be performed in m times n ways, right? And so that's what we saw with our slots. So this is what we found. Found it. I combined it using our slots. Mhm. Whee! Eek. License plates, another super common combinations problem. And we love to put restrictions on some of the letters. We also know that there are some combinations that they pull, right? But those we're gonna ignore, right? And so here, we learn a little bit of how to deal with these license plates. Okay, so a truck license plate consists of a letter, okay? And just so we're tracking, there are 26 letters, okay? And so here, followed by a letter, there are 26 letters, followed by 4 digits. Okay? Now we have to be careful here because how many digits are there?
No.
4,
Wait.
10. Nice. But that's what gets everyone all the time, right? So 0, you could have a 0 on your license plate. I do. Well, is my license plate. WE0. Well, which I thought was really fun. But there are 10 digits, right? 0, 1, 2, blah, 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 blah. But you max out at 9. Right? Which takes us from our digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Technically, that's where it came from. Yeah. How many such license plates are possible? So now I'm counting how many different ways can I set this up. Now I do not want to make a tree for this. You can, but we could solve this problem just using our slots or the multiplication axiom if you want to be fancy about it. So we can solve this using our slots. So we're told the breakdown of all these license plates, right? It's followed by, it starts with a letter. And then 1, 2, 3, 4 digits. Digit, 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 digit. Someone auto-tune that quick. Digit, 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 digit. But knowing how many digits there are and how many letters there are, right? A license plate has to be complete. So it has to have a letter and a digit and a digit and a digit and a digit. I feel like I'm onto a rap tune here. It's gonna break through. So I have 26 times 10 times 10 times 10 times 10. It's a lot of license plates. I get 1, 2, 3, 4. Okay, good. 2, 6, 0, 0, 0, 0. It's a lot. It's not that many though. Think about how many trucks there are, right? And we have that too. Our trucks have a different format than our cars do, right? Trucks have 2 letters followed by 4 numbers, whereas the new license plates are alpha, alpha, numeric, 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 alpha. Old plates used to be 3 letters, 3 digits, and the super old plates, or I can never remember if it's the other way around, were 3 digits followed by 3 letters, but they changed it. I've been obsessed with license plates for a long time. Now you know. The more you know. So, okay. But there are 260,000 license plates like that. This is kind of annoying too.
Therefore.
How about a true-false situation? In how many different ways can a 3-question true-false test be answered? We have 3 questions. We're going to answer question 1 and question 2 and question 3. Now, the reason I know to put the question numbers at the bottom is because for each of those, I have 2 choices, right? And the number of options that I have should go on top, right? Whereas I'm not choosing to just answer one of the questions, one of the 3 questions, right? And so that's why I have to choose an answer for question 1, and then I'm going to pick an answer for question 2, and then I'm going to pick an answer for question 3. Let's assume that no one is leaving a true false blank, right? It's an option, I guess. That would make it 3. But let's assume no. Let's assume that they're going to answer. It breaks my heart when I see an empty multiple choice question. What? Are you kidding me? Assume an answer must be given. I should. This is how my supervisor published an article a long time ago, and he had 2 versions of a multiple choice test, and someone had done really well on the other version, but really poorly on their version. And they said, no, I didn't cheat, of course not. And then this is how we can find the probability of that happening, just by guessing, right? You can figure out how many different combinations there are, and then you just happen to pick one of those, right? More likely they got it from their buddy. Anyways, boring. True, false. Since we're assuming that they have to give an answer, I have 2 options. And for question 2 and question 3, I get 8 different ways. Right? 8 different ways that I could answer that quick 3-question true, false. This is all I have for today. And homework. It's turning into one of those classes where you get your homework done in class. I know. Nice. Crazy. Got a little ways to go though. If you have 4 people now and 4 seats, what are your slots? So you've got 1, 2, 3, 4 seats in a row. Seat 1, 2, 3, 4. Let's just say that they're gonna sit down, or we're gonna sit them down in seat 1 first, and then seat 2 first, and then seat 3, and then seat 4. Shouldn't have said that first again. Ugh. Can a person sit in 2 seats? No. Which means that I have 4 people that I can choose from for my first seat. Exactly. But I have 3 people, right? Because 1's already seated. Now I'm altering how many I have to choose from, right? And so on. 3, 2, and then 1. Fine, you're last, you have to sit at the end. So sometimes, right, there will be restrictions on these counts that we have above, right? But we can just adjust those, right? Okay. Can I just, I'm pretty sure we need it anyway, so I may as well introduce it here. Or did I cut that section? That'd be so nice. This 4 times 3 times 2 times 1 is 24. Do you guys remember factorials? Or maybe not, maybe you haven't seen them. Factorials. This can be written as 4 factorial, really 4. Oh. This is called 4 factorial. We're not supposed to introduce it until a later section, but I think it's nice to see it here, right? And just kind of to see it in action, how we decrease by 1, right? And so in general, n factorial, whoops, I should clean up that. N factorial is n times n minus 1, all the way down to 3 times 2 times 1. You just multiply through, starting with the first one and then decrease by 1. Right? And a lot of your calculators have the factorial button. Many calculators, I'd say any scientific calculators, have an n factorial button. Or is it, what's mine called? No, I can't see it. Weird, I really don't see it, but that's okay. I know it's on there. Now it's driving me bonkers. I know it's on here. Okay, that's okay. And you can try it. 4 factorial should be 24. Unless I did weird math. 4 times 3, 12 times 2, 24. how many 3-letter word sequences can be formed using the letters A, B, C if no letter is to be repeated? So we have 1, 2, 3 letters. And this is the same situation, right? I can't have a person sit in 2 spots, and I also can't repeat a letter, right? And so now I'm going to have all of A, B, C to choose from for the first one. So I have 3. And then I've used up one of those 3, and it doesn't really matter which one I've used up, right? Because I have 2 remaining. And then last, I have 1. So 6. But only some of those are words, right? But we ignore that. Okay. Oh my gosh. It's kind of embarrassing. Am I? I could do another section. But do I have it in me? I didn't read it. Or I didn't like memorize it. I've read it. No, that's juicy, right? Oh my gosh. Let me see here. Yeah, but we've already done like half of it. Okay, are you guys ready for it? Should we just go for it?
Yeah.
I'll do it.
Don't think I-
Yeah, don't think I won't. Well, so that's the rub, isn't it?
It won't be a bonus.
It would be better for my special situation, wouldn't it? All right. Let's see if it'll behave. Hey, this is the wrong. Boo. Okay. Okay, while I get this sorted. You guys can check out the homework. Okay. It's actually a perfect follow-up. Because in example 7.2.6 of section 7.2, we were asked to find the word sequences formed by using the letters A, B, C if no letter is to be repeated. It's the one we just did. Nice. And we could use a tree diagram to get the arrangements. I know, right? Let's see here. Slots are good. Uh-oh. Okay. I don't know why I'm feeling so caught off guard. Thanks.
We still have it all.
I know, but is it enough? At this rate, we can cut Thursday, we can cut Tuesday. Okay. Here, we didn't repeat any letters. No. And okay, fine. I am gonna try this. Copy.
You can do this.
So annoying. Okay, let's try. I think my iPad maybe needs a little kick in the pants. What's the tree look like? Letter 1 in a 3 letter word. A, B, C. Now for my letter 2, oops, I only have 2 choices because I can't repeat A. So then I only have B and C to choose from. If the first letter is B, then I only have A and C to choose from. And if the first letter is C, I only have A and B to choose from. And then for my final letter, right, I have to figure out which one I haven't used yet. And so then I have letter 3. Oh, I did this sloppy, didn't I? Oops, but there's only one. I'll tilt them off to the side here just to emphasize that it's not one long branch. There. AB must be C. AC must be B. BA must be C. BC must be A. CA must be B. Hey, that's a word. And CB must be A. Could also use this to figure out if there are any words. I only see cab, but that's okay. Abk, akb, back, baka, cab, kba. So here, the order of the letters in the words is important, right? And so that's what permutations are, where the order is important, and I'll underline that part. Can I highlight and underline in the same move? I guess. So if order is important, right? Whereas when we were thinking about our blouses and our skirts and our pumps, it didn't matter which order I chose those in, right? They just generate an outfit in the end, right? Choosing my skirts first and then my blouse and then my pumps doesn't generate a different outfit than choosing my pumps first and then my skirts and then my blouse, right? Whereas here it matters which letter was first, which letter was second, and which letter was third. Yeah. And so these are called permutations. So they're kind of a special case. Let me snag this. Special. Oh. Cropped up this. And you know what? Make it even bigger. So a permutation is a set of elements that are in an ordered arrangement. I went rogue there. Where each element is used once. Nice. I know, right? We're getting there. How many three-letter word sequences can be formed using the letters A, B, C, D? Now we have three-letter words, right? So that is still going to be we can still have our slots as long as we remember that. Oh, now I'm trying to remember. Did she not say the repetition on purpose, or did she forget to? These are things I would have memorized. No, there's no time. I need to study. Looks like she just forgot to say it. Assuming no repetition. Feels important to say because that's what we're talking about. Yeah, that was my first clue, I guess. Letter 1, 2, 3. Three-letter word sequences, but I have 4 to choose from, so that's nice. So that means that I have 4 first. Then I decrease that by 1 because I've used one of those. And then I have 2. I'm getting 24. 4 times 3 is 12 times 2 is 20. Nice. So that would be a permutation. Here's a doozy. How many permutations of the letters of the word article have consonants in the first and last positions? Rude, right? So now you're taking these letters and you're figuring out how many ways can you rearrange all these letters, right? Forcing consonants in the first and last positions. Have a think on it. Try it out. To get you started, I would make my slots over the word. You can do whatever you want. But for me, I think that's the easiest. My consonants are R, T, C, and L. What's the Wheel of Fortune? R, S, T, L, N, E? Are those the letters that you get for the final spin of Wheel of Fortune? Come on, guys. They give you some of the most common letters. I feel like it's R, S, T, L, N, E. I'm counting 4 consonants. But I'm forcing this first letter and the last letter to be one of those 4. right? And so what I'm gonna do is I'm gonna say, and it doesn't matter because we know we're gonna end up multiplying, right? 4 times a bunch of stuff, then times 3 is the same as 3 times a bunch of stuff, then times 4. And so I think it's just easier to tackle the 4 first and then the 3 at the end. So I have 4 consonants to choose from. And then I have 3 consonants to choose from. I have 1, 2, 3, 4, 5, 6, 7 letters total. But I've forced 2 of those into positions, right? And so kind of the curveball, I guess, is I only have 5 to pick from there, right? Because I've already taken 2 of those and I've put them in their places. And now I have 5 to play with, right? Which includes the remaining consonants, doesn't matter which ones they are, and the vowels, right? And then from here, there are no other restrictions, right? And so now I have 5, 4, 3, 2, 1, which is good because one of those I need it to be 1, otherwise I'm missing a slot somewhere, right? Because I want to redistribute all these letters. So how many ways? Times, 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 times. 4 times 5 times 4 times 3 times 2 times 1 times 3. I get 1,440 different ways or arrangements of the letters in the word article. I know. Makes you think of Wordle, right? What's Wordle? Well, we're allowed to have repeats, right? But it reduces the number of combinations if you know clues about the word, right? The letter. Okay, nice. That one's tricky, right? But once you know this trick of, okay, if there are restrictions, let's handle those restrictions first, right? And then make the adjustments for the remainder, and then you're good to go. Good to go, she says. I'll do this on the next page. Now we have 5 letters, A, B, C, D, E. The number of 4, so we're going to find the number of 4-letter sequences, 3-letter and 2-letter word sequences, and we assume, assume no repetition, which is kind of safe because we're in the permutation section. So I have 5 letters, and I'm going to start saying permuted into 4 spots. And so here we can do our slots, 1, 2, 3, 4. And for my first one, I have 5 choices, then I have 4, and then I have 3, and then I have 2. I think we're pretty good at these now. Feels good. 120. I'll confirm. Oops, times 32. Yes, nice. So let's introduce some. Therefore, there are 120 permutations, or I should say 4-letter permutations of 5 letters. Right. From those 5, if I want to permute them into 4-letter permutations, there are 120 ways to do that. B, now I have 3-letter word sequences. Same thing, right? I start off with 5, and then I have 4, and then I have 3, and then that's it. Oops. And the number of 2-letter word sequences. Now I have just 20. Still a lot though. Yeah. The tree for this one is kind of gross. Think about it. Right? 5 branches, and then you'd have to adjust the later branches based off of your first branch because you're not allowed to repeat anything, right? And so it's nice to have the slots, which is why I like to just introduce them right away. Then you'll get really good at the slots, and then you don't need anything else. Oh. NPR. So here, how we phrase this is we said there are 120 4-letter permutations of 5 letters, okay? Or 5 permuted into 4 slots, right? And so here, or 5 letters permuted into 4 slots. The next one, we had 5 letters permuted into 3 slots. Okay? And so here we have 5 letters permuted into 3 slots. And finally, here we have 5 letters permuted into 2 slots. This 5P2, 5P3, 5P4, we're going to write like this. 5P4, right? 5 permuted into 4 slots. 5 permuted into 3 slots. Let me just check here. And 5 permuted into 2 slots. Or in general, we call it NPR, which is usually what the button is on your calculator. And so, but NPR uses the factorial. And so we need the factorial, but we've already seen it, right? And so it's not too bad, but n factorial, really n, is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. And as a fact, 0 factorial is 1, which is kind of confusing, but we need that in order for things to work. Nice. So what is the formula then? the number of permutations of n objects taken R at a time, right, is going to be NPR. Now, you're allowed to use your calculator button. You have an NPR button, no doubt. Yeah. And so you can confirm it, but I do need you to know your way around this formula. Okay? And so let's have a look. NPR is shorthand for, what did we just do? If we establish that 5p4, right, then we had 5 times 5 minus 1 times 5 minus 2 times 5 minus 3, and we have R slots, right? And so what we can do is we can mirror that and say, okay, if I have 5 times 4 times 3 times 2, right, then that makes my R 4. I think I jumped too far ahead. Consider what we know, 5p4 is 120, right? And we got there by saying, okay, we have 1, 2, 3, 4 slots, and I had 5, and I'm going to write 5 minus 1, 5 minus 2, and 5 minus 3. Slot 1, 2, 3, 4. So if I am permuting into 4 slots and I end at 5 minus 3, that 3 is kind of related to the 4, right? And it's related in a way where, so here, R is 4 and N is 5. So N, we end at N minus R plus 1. In this case, is 5 minus 4 plus 1. 5 minus 4 plus 1 is 5 minus 3, right? Or like we ended at 2, right? Or 5 minus 3 is 2. And so the general formula for NPR, your calculator would just do this in the background, right? The formula that I need you to know for NPR is this one. Well, I'll give it to you on your formula sheet, right? This will be on your formula sheet. This is as much for me as it is for you, so I remember to put it on there, hopefully. No, I will. Yeah. So technically this is true, right? And that's what we use to be able to do these problems anyways, right? Even without the formula. So you'll still be able to do the problems. It's just that using the factorial is going to be a little bit easier. Okay. Now, NPR is n factorial over n minus r factorial. If we consider 5p4, and I replace my n's with 5s and my r's with 4s, it's nice because we know this answer is supposed to be 120, right? 5 factorial over 5 minus 4 factorial. This 5 has a little bit of a flare on it there. 5 factorial is 5 times 4 times 3 times 2 times 1. Five minus 4 factorial is 1 factorial. 1 factorial is just 1. So I don't get very far, but I can cancel these guys. And then I'm just left with 5 times 4 times 3 times 2. But notice that that's what we already found with the slots. So that's what I mean. You can always solve these problems with the slots. And so notice we already found this. With the slots. What if we have to compute the following using both formulas? Like I said, I need you to be kind of nimble with the formulas. You can already solve these problems without the formulas, but just being able to manipulate the formulas is good. Slash something I need from you. 6p3. In terms of the first formula, let's write it out. Wherever you see an n, you're going to replace it with a 6. And whenever you see an r, you're going to replace it with a 3. And so 6p3 is 6 times 6 minus 1. And just to figure out when I need to stop here, I'm going to figure out my endpoint. Right? So here, this is 6 minus 3 plus 1, which is when? 3, 4? I'm getting close already. Or 6 minus 2, I guess. Maybe that's easier. Because then I know I stop at 6 minus 2, which is my next stop here. You can also think back to your slots, right? The 3 tells me I have 3 slots, right? And the 6 tells me how many things I have to choose from initially, and then I'm not allowed to repeat any, right? And so, or my slots, 1, 2, 3. And I have 6 initially, 5, 4. It's going to be 6 times 6 minus 1 times 6 minus 2. 6 times 5 times 4. Either way, I'm going to get 120. Wait, again? The heck? I'll check it with my calculator function. It's true, it's 120 again. How about with the other formula? This formula here. Six p3. Whenever I see an n, I replace it with a 6. 6 factorial divided by 6 minus 3 factorial. First, I'm gonna simplify this. 6 factorial over 3 factorial. And then I'm gonna do something sneaky. My numerator is 6 times 5 times 4 times 3 factorial. If you want to be lazy about it. Why did I stop at 3 factorial? Because then I can cancel it with the bottom. Right, and so here's the sneaky part is 6 times 4 times, or 6 times 5 times 4 times 3 factorial. 3 factorial is 3 times 2 times 1, right? But if I stop at 3 factorial, then I know I can cancel it with the denominator, which is also 3 factorial. So that's what lets me cancel these two. And then I'm just left with 6 times 5 times 4, which is what we've been landing on. About 7p2, right? 7 things permuted into 2 slots. Right? If you read it that way, we can use our slots to figure out what answer we should be getting. Slot 1, slot 2. I have 7 things and then I have 6 things. So I have 42 different ways to permute those. So now, using our first version of the formula, so I guess I'm solving it 3 ways. Showing off, I guess. We only had to do the 2 ways. If n is 7, 7p2, and r is 2, then I need to figure out when to stop. And I'm going to stop at 7 minus 2 plus 1. So at 7 minus 1. I think, unless I'm thinking bad. Is 5 plus 1. I am thinking bad. Sorry, guys. 7 minus 2 plus 1 is the same thing as 7 minus 1. Sorry, I was thinking really bad. 7 times 7 minus 1. Right, this tells me to stop here. Makes sense because I only have 2 slots. Just had to get there. 42. Can use this for poker hands, right? How many cards do you have? If you know what cards you have, that eliminates cards, right, from other hands. So on. So with this formula, 7p2 is 7 factorial over 7 minus 2 factorial, which is 5 factorial, which means I'm going to stop at 5 factorial, right? I'm going to stop writing at 7 times 6 times 5 factorial divided by 5 factorial. I stop there because I know I'm about to cancel these. Bink, bink. Left with 7 times 6, which which is still 42. In how many different ways can 4 people, and right, we've already seen people, you can't repeat people if there are seats, which there will be seated in a straight line if 2 of them insist on sitting next to each other? How's this for problem solving? How are you going to solve it? So you've got 4 people, let's call them A, B, C, D. And they each get a seat, it sounds like. And so we can have seat 1, 2, 3, 4, but there's a restriction. Let's say it doesn't matter which 2 insist on sitting next to each other, right? But let's say A and B are saying, hey, we have to sit next to each other. We're BFFs. Say A and B must sit together. I could have sit A down first and then B. Or, and we're gonna work through this, right? I could scoot these guys over, right? Or they can sit like this. What's another alternative? Totally. Yeah, we can start over. Right? They have to sit together. They have to sit together. They have to sit together. So what if we treat A, B, and B, A as one thing? Okay. And let's see, am I forgetting something? We can sit seat. How about this? We can treat A and B as one person, right? Taking up 2 chairs. Which kind of eliminates a chair, right? And so we can seat A, B. Right? Then for my first seat, right? Because A and B are now one thing, they have to sit together. Right? And so now I have A, B to choose from, or C or D, right? So I have 3 choices for my first seat. And then I have 2 choices, and then I have 1 choice. seat 1, 2, 3. Or, it's our first or. Or we can seat first B, then A, right? That's going to be different. That's a different lineup of people if you kind of imagine it, right? And so now, or we can seat B, then A. That's going to look the same in terms of the math, and there are 3 times 2 times 1, which is 6. And seat 1, 2, 3 still has 3 times 2 times 1 options, which are 6 options, but they're different options. And so the total, right, where we first seat A and then B, or we have to consider seating B, then A, right? So the total number of seatings, is 6 plus 6, which is 12. And in general, when you catch yourself saying or, we add those counts. So or means addition, right? And means multiplication, and or means addition. Nice. That one's a tricky one. Something to have in our tool belt. Wow. Can't believe we did it. All because you believed in me. You have 4 math books and 5 history books to put on a shelf. That has 5 slots. In how many ways can the books be shelved if the first 3 slots are filled with math books and the next 2 slots are filled with history books? Kind of funny to have slots in the question as well, but I would probably just map this out and solve it using our slots, right? We've got some restrictions on what we can use in which slots, right? But besides that, we have 5 slots. 2, 3, 4, 5. Okay. The first 3 slots have to be filled with math books. So here, these have to be math, where I have 4 math books to choose from. And then these ones, the next 2, have to be filled with history books. So from the 4 math books, I start with 4 and then I've used 1, so then I have 3 and then I have 2. And then for history, I have 5 history books, but only 2 slots. And so I have 5 to choose from first, and then I have 4. We can get the answer: 4 times 3 times 2 times 5 times 4. I get 480 different ways that you could arrange your bookshelf in that way. Notice, though, that each of these components, the math component and the history component, are permutations, right? And so this would be the same thing as we have 4 permuted into 3 slots. And 5 permuted into 2 slots. So what you could do is you could use your P button on your calculator and PR button on your calculator, right? I find that that's kind of difficult. I find that the slots really lend themselves to solving all of these problems, right? As long as you consider all the situations. But you could, so you could say, so we could solve this by 4p3 times 5p2, which I really hope 4p3 times 5p2 is 480. It is. But the slots will work. And I'm happy if you're able to use the slots. This stuff is tricky, right? But practice, you'll see patterns emerge. Did it. Wow, crazy. And you guys did it, hung in there. Good job. I was gonna skip 7.4 and I still will actually, because what is it? It's permutations, but in a circle. So you can read it if you want to, right? But then you've got restrictions on a circle instead of in a line. I think a line is plenty. But you can do it for a circle. Yeah. Fun. If you have any questions, let me know. Otherwise, I release you. Wow. And 2 sections for homework? Oh my gosh.